I recently talked about two different bracelets where I'd like to analyze the permutations that arise from them. This is the second, and what I think is the harder one to analyze. This bracelet has 8 directed black beads and 8 directed red beads. Thanks for watching. This problem is inspired by a bracelet we got during October. There are 8 black skull-shaped beads interlaced with 8 red skull-shaped beads. We want to know how many different bracelets are possible if we took apart and reassembled the bracelet with the beads in any possible arrangement. We note that for bracelet permutations, we cannot tell apart rotations and flips of the bracelet. One thing that makes this different than an ordinary bracelet permutation is that the skulls are directed, so we're able to tell if they point clockwise or counterclockwise. Since that's not part of the usual bracelet permutation, we'll analyze the problem with and without directed beads. I'll give the answers right here up front. For the traditional bracelet permutation, where the skulls are replaced with spherical non-directed beads, 440 different bracelets are possible. On the other hand, if we take into account the fact that we can tell which way each skull is pointing, there are 26,362,807 possible bracelets. One thing about these bracelet totals is that they include bracelets that are not all equally likely if the bracelet is assembled randomly. We'll talk about relative frequencies in the details ahead. So let's talk about how we got these numbers, and for this problem, we'll need to introduce some concepts and topics from group theory. Group theory was originally developed to study symmetries and permutations like the ones that arise in this problem. If you want to analyze a different bracelet where group theory isn't necessary, check the video where I analyze a bracelet with 19 orange and 19 silver beads. It's easier because 19 is a prime number. So what is happening in any bracelet permutation is what is called a group action. A group of moves is acting on the beads on the bracelet. The group in question is called the dihedral group of 32. It's important to remember that the group is a set of 32 moves, not a set of beads or bracelets. The group acts on the beads of the bracelet by letting each of its 32 moves transform the bracelet from its arbitrary initial position, one by one, into all 32 possible positions, 16 on one side and 16 if the bracelet is flipped over. Sometimes all 32 positions will have different arrangements of colors on the polygon. Other times there will be fewer arrangements of the colors generated due to symmetry. It turns out that in order to take the fixed permutations of 8 red and 8 black beads and convert them into a bracelet permutation, we need to group the fixed permutations, which I will call bracelet arrangements, into sets of arrangements that correspond to the same bracelet. Symmetry determines how many arrangements will correspond to a given bracelet, and symmetries are related to subgroups. Since the subgroup structure of the dihedral group of order 32 is important in the analysis, we'll show it here. On the left column are cyclic subgroups, consisting only of rotations, no flips, and the identity, which can be thought of as a rotation through 0 degrees. The arrows show that cyclic subgroups are subgroups of every group of higher order. Next, colored green are subgroups that consist of flips that go between the beads, as well as some rotations and the identity. Further to the right, colored yellow are subgroups of flips that go directly through the vertices where the beads will be seated, as well as some rotations and the identity. The good news is that the group theory needed to analyze this problem is very basic, maybe the first chapter or two in an introductory textbook. It's important to know what a subgroup is and that the order of the subgroup evenly divides the order of the group. If you know what a normal subgroup is, you'll see that it acts upon bracelets in a slightly different way than non-normal subgroups. So let's talk about what symmetry is in a more precise way. We're requiring that every bead of the bracelet resides on the vertex of a 16-sided regular polygon. That's not a problem. Just spread the beads out evenly around the circle and that'll do it. Once this is done, we can let the dihedral group of 32 operate on the bracelet. The group contains all 32 moves that'll put the bracelet into all 32 different positions, all of which have a bead on the vertex of the polygon. It does this by rotating through multiples of 22.5 degrees, or flipping the bracelet along one of the 16 lines of symmetry. We'll say that the bracelet has symmetry if at least one of these moves, other than the identity, preserves the color of each vertex of the polygon. In other words, if a new bead has arrived at a vertex, it is the same color as the old one that was there before the move. For example, in the bracelet pictured, the move corresponding to a rotation of 45 degrees is one of many moves in the dihedral group of order 32 that preserves the color of each vertex. Thinking more about which moves preserve the color of each vertex shows that half of the 32 moves preserve them, and half of the moves do not. Those ones that do not consist of 8 edge flips and 8 rotations through odd multiples of 22.5 degrees. Turns out that for any arrangement of beads sitting on the vertices of the polygon, the set of all moves that preserve the color of each vertex is a subgroup of the dihedral group. The proof involves noticing that for any two moves that preserve the color of each vertex, then the product of those two moves in any order preserves the color of each vertex, since each move changed nothing. We have closure of a finite subset of the group, and therefore it contains every power of every move, therefore the inverse of every move, therefore the identity, therefore it is a subgroup. So we can find all symmetries in a systematic way by going through all the subgroups on the diagram and deducing which arrangement of colors on the vertices are preserved by the moves in each subgroup. The parent dihedral group of order 32 contains 16 flips and 16 rotations, one of which is the rotation through 0 degrees, also known as the identity. Half of the flips go between beads, and we'll call these edge flips. The other half of the flips go through beads, and we'll call these vertex flips. We note that our bracelet cannot have symmetry under the dihedral group of order 32, since it has moves that send any given bead into any other given bead, and therefore all beads must be the same color for symmetry under this group. Moving on to subgroups of order 16, let's start with the cyclic group. It has a rotation of 22.5 degrees clockwise that moves every bead to its immediate neighbor. Therefore, every bead must be the same color in order to have symmetry under this subgroup. Let's move on. Next up, the dihedral group of order 16, consisting of 8 flips that go between beads, as well as rotations through an even number of notches, and the identity. Since there's a line of symmetry between any two neighboring beads, any arrangements of beads having symmetry under this subgroup must have all beads the same color. The same story. No symmetry found yet, so let's move on. The next dihedral group of order 16 consists of the 8 flips that go through beads instead of between them, as well as rotations through an even number of notches and the identity. Lines of symmetries go through the beads and force every bead's two neighbors to be the same color, and the result is two interlaced sets of 8 beads, where the 8 beads in each set have the same color. There are 2 ways to achieve symmetry with the colors we have, one set red and the other black, and vice versa. Obviously this is the same bracelet in 2 different arrangements, so let's explore what's going on and see what to expect as things become more complicated later in the analysis. We can formalize the definition of a bracelet to be the set of all possible arrangements of beads corresponding to it. This subdivides the set of all arrangements of beads on the vertices, which is just an ordinary permutation, into equivalence classes consisting of all arrangements corresponding to a physical bracelet in all 32 of its orientations. Importantly, these sets of equivalence classes will have a number of arrangements which evenly divides the order of the parent group, and for us this means powers of 2, from 1 to 32. Also worth noting is that as we go through the subgroups from largest order to smallest, if an arrangement with symmetry appears for the first time in a subgroup of order n, then it corresponds to a bracelet that has 32 over n arrangements. Here we have 2 arrangements of the alternating bracelet appearing for the first time in a subgroup of order n equals 16. 32 over 16 is equal to 2. These 2 don't necessarily have to appear in the same subgroup, but since this is a normal subgroup, all arrangements of that bracelet are in the same normal subgroup. Now we move on to subgroups of order 8. Symmetry under the cyclic group of order 8 requires that every other bead must be the same color. The 2 possibilities are exactly the same as we got under the last subgroup we looked at. Since cyclic group of order 8 is a subgroup of every group of higher order, it must contain all the arrangements we found in previous steps. In this case, it has those 2 arrangements and nothing more. Now let's move on, but we'll do 2 subgroups at once. The 2 dihedral 8 subgroups of the dihedral 16 subgroup in which its flips go through edges. Each contains 4 flips evenly spread but aligned differently. The moves in each subgroup define 2 sets of 8 beads, which must be the same color in order to have symmetry. We've been in that situation before, but now the 2 sets of beads look a little different. Instead of single alternating, they're double alternating, but there are still 2 possibilities of colors for each subgroup. In this row with n equals 8, there must be 32 over 8 or 4 arrangements for each bracelet. They're not all in the same subgroup. In fact, we have our 4 arrangements of this bracelet spread out over 2 subgroups. This is what happens when the subgroups are not normal subgroups. Now for the final two subgroups of order 8, dihedral subgroups of D16 with flips that go through vertices. It defines a set of 8 beads shown in yellow, which must be the same color, and 2 sets of 4 beads shown in white and blue that must be the same color. We have 8 beads of each color, so this means the 2 sets of 4 must be the same color, and we have the same situation as 2 sets of 8. Sets alternate, and with only 2 possibilities, they're the same 2 arrangements as found in the parent subgroup right above them. So there's no new bracelet here. Down to subgroups of order 4. Again, we start with the cyclic group. Every 4th bead must be the same color, and this defines 4 groups of 4 which have the same color. We must pick 2 of these 4 groups to be red and the other 2 to be black, and there are 4 choose 2, or 6 ways to do this. Included in those 6 ways must be all the arrangements we already found, since the cyclic group of order 4 is a subgroup of all groups of higher order. Indeed, we have exactly 6 arrangements found so far, 2 from the alternating and 4 from the double alternating, so there's no new bracelet to be found for the first time in C4. Now let's look at the 4 D4 subgroups with edge flips. We look at these 4 at the same time because they are not normal subgroups, and any bracelets found will have their arrangements spread among these subgroups which are identical except for the alignment of their flips. These, like the cyclic group of order 4, define 4 sets of 4 beads which must be the same color, and again there are 6 ways to do this. Since each D4 has only one parent group, we need only account for the 2 arrangements found in its D8 parent, and this yields 4 new arrangements per D4 subgroup. All the 4 D4 subgroups with edge flips taken together yield 16 new arrangements. In this row we have n equals 4, so that 32 over 4 equals 8 arrangements per bracelet. We therefore expect 2 new bracelets over these 4 subgroups, and with little effort we can find them. I'll call the one on the left the quadruple alternating, which is obvious, and the one on the right paradiddle, because this pattern is the same as for drummers who do that drum exercise called the paradiddle. Closing out the subgroups of order 4 are 4 dihedral 4 subgroups with flips going right through the vertices. Symmetry under any of these groups breaks beads down into same color sets of 4, 4, 4, 2, and 2, which for us is the same as 4, 4, 4, and 4, since we don't have exactly 2 or 6 beads of a color. Again, there are 6 patterns for each, 4 of which are new, times 4 subgroups for 16 new arrangements, divided by 8 arrangements per new bracelet in these subgroups, yielding 2 new bracelets with symmetry under these subgroups. Interestingly, this is a pair of bracelets for which exchanging red and black beads gives the other bracelet. One might actually mistake these for the same bracelet, but they are different, because the 3 same color beads in a row is black for one and red for the other. Now down to subgroups of order 2, the final row of subgroups. Cyclic group of order 2 defines 8 pairs of 2 beads, diametrically opposite pairs, that must be the same color. There are 8 choose 4 ways, or 70, to choose these pairs half red and half black, so 70 arrangements. Cyclic group of order 4 is a subgroup of all groups found so far. These 70 arrangements include all the arrangements found so far, so the new ones will be given by subtracting the 38 arrangements from the previous steps. This gives 32. Wow, a power of 2. We're in a normal subgroup, so all 16 arrangements of any new bracelet in this group must be there as well. So good thing we got a multiple of 16, right? There are 32 over 16, or 2 new bracelets, and with some thought and trial and error, you can find them. Here they are. Moving on to the 8 D2 subgroups with a single edge flip. Again, 8 same color pairs are defined for a total of 70 arrangements possible with symmetry. There's only one parent subgroup contributing arrangements, and it contributes 6, so subtract and get 64, amazingly a power of 2 again. There are a total of 8 D2 subgroups like this one, yielding 512 arrangements, and dividing by 16 arrangements per bracelet in this row, we get 32 new bracelets. It's hard to enumerate all 32, but a few representatives are easy to come up with. The remaining 8 D2 subgroups with a single flip through the beads, like every other subgroup in this row, defines 8 sets of 2 beads that must be the same color, giving 70 arrangements. Subtracting the 6 arrangements which were in the parent subgroup gives 64 new arrangements. Since there are 8 subgroups like this one, there are 512 new arrangements, and at 16 arrangements per bracelet, there are again 32 new bracelets. It's hard to enumerate all 32, but a few representatives are easy to come up with. Now we're done with symmetry. The remaining bracelets will have no relevant symmetry and will have 32 distinct arrangements as the 32 moves of the D32 group acts upon them. We compute the total arrangements for all bracelets as 16 choose 8, giving 12,870. We had one bracelet with 2 arrangements, one with 4 arrangements, 4 bracelets with 8 arrangements, and 66 bracelets with 16 arrangements, for a total of 1,094 arrangements with symmetry. This leaves 11,776 arrangements without symmetry, and magically this is exactly divisible by 32 arrangements per non-symmetric bracelet to give exactly 384 bracelets without symmetry. It's a simple matter now to tally the results. Total bracelets is 440 as shown. Relative frequencies are in proportion to the number of arrangements the bracelet has when acted upon by the dihedral group of order 32, and therefore proportionally lower for bracelets with more symmetry. As they must, relative frequencies sum to 1. Ready for directed beads? Don't worry, in a way things are a little easier since a directed bead cannot have a line of symmetry going through it. The line of symmetry reverses the direction of the bead, and therefore the appearance of the vertex changes. We cut down on about half of the subgroups we need to analyze, but we're also going to have larger numbers as we introduce powers of 2 for the directions of the beads, and the bracelets are more complicated, so we have a hard time thinking of what the bracelets might be as we try to enumerate the bracelets whose precise number is predicted by group theory. For subgroups of order 16 and larger, we have nothing. This is because for non-directed beads we got nothing except for the subgroup with vertex flips, and vertex flips are now out. So let's move down to subgroups of order 8. First, the cyclic group. This breaks down into 2 sets of 8 alternating colors, and there are 2 ways to do that. Then there are also 2 sets of alternating directions in which we get to choose clockwise or counterclockwise independently for each, and thus a factor of 4 for a total of 8 arrangements. Cyclic subgroups are normal, so we expect to find all 4 arrangements of each new bracelet in that subgroup, so let's look for 8 divided by 4, or 2. Here they are. Each has the alternating color pattern. One has beads all facing the same direction. The other has beads alternating direction. Now for symmetry under the dihedral group of order 8. There are 2 subgroups identical except that the flips are offset by a rotation. Any bracelets we find here will be spread over the 2 subgroups. Colors and directions are divided into 2 groups of 8, so we have 1 choice for the color, and then for the directions, we have 4 ways to choose clockwise or counterclockwise for each, a total of 8 arrangements. There are 2 D8 subgroups, so this is 16 arrangements divided by 4 arrangements per bracelet, giving 4 new bracelets. With some thinking, we can enumerate the 4, and here they are. Each has a double alternating color pattern, like its non-directed counterpart. Then there are 4 ways to arrange the pairs of arrows to preserve symmetry as shown. Down to subgroups of order 4, cyclic group first as usual. 4 sets of beads which must be the same color and direction. This implies 6 choices for color and 2 to the 4th power or 16 for direction. Product is 96. Since C4 is a subgroup of all higher order subgroups, we must subtract all arrangements already found, which consist of 6 bracelets of 4 arrangements each, or 24, leaving 72 new arrangements. This is a normal subgroup, so expect all 8 arrangements of any new bracelet to be here. This means there are 72 over 8, or 9 bracelets with symmetry under C4, predicted by the theory. It's getting harder to enumerate these, but let's try. Here are 3 with an alternating color pattern. In the first 2, all arrows point the same way, except for every 4th arrow in retrograde. The color of the retrograde arrow distinguishes the 2 bracelets. The 3rd bracelet is a double alternating arrow pattern on top of a single alternating color pattern. The final 6 of 9 predicted bracelets have a double alternating color pattern. There is a unidirectional bracelet, one where beads of each color are unidirectional but opposed direction, and the final 4 are combinations of one unidirectional color versus the other color pointing in or out. And because these are getting more intricate, these are the last bracelets I'm going to show. We'll let the theory determine the number of the rest of them. Moving on to D4, there are 4 subgroups identical except for the offset angle of their flips. Each breaks down into 4 sets of 4 beads which must be the same color and symmetric direction. Again, 96 possibilities. Subtract the 8 arrangements inherited from the parent to get 88 new arrangements in a single D4 subgroup. then times 4 subgroups and divided by 8 arrangements per bracelet gives 44 new bracelets. No enumeration, we'll just trust the theory. Down to subgroups of order 2, the final row. Under the cyclic group of order 2, we have 8 sets of diametrically opposed beads which must be the same color and direction. We have then 70 color combinations times 256 directions. C2 is a subgroup of all higher order groups, so we'll subtract all of the arrangements found so far to get 17,472. It's a normal subgroup, so we expect all arrangements of any bracelet found here to be also here, so divide by 16 arrangements per bracelet to get 1,092 new bracelets in the cyclic group of order 2. Trust the theory, it works. Finally, D2 also breaks down into 8 sets of 2, also 70 times 256 arrangements, but this time just one parent subgroup contributing 96 older arrangements, so we've got 17,824 new arrangements per subgroup. Multiply by 8 subgroups and divide by 16 arrangements per bracelet in this row, and there are 8912 new bracelets. Trust the theory. Now we're in the home stretch. We find the total arrangements using fixed permutations for the colors and 2 to the power 16 for the bead directions. Big number in the high 100 millions. Subtract the bracelet arrangements with symmetry, there's a total of 160,512 arrangements. Just a rounding error compared to the hundreds of millions of arrangements in total. But this is a precise discipline. It feeds results into other precise disciplines like number theory, and there's no rounding when a difference of 1 is the difference between a prime number and a composite, no matter how large. So subtract the 160,512, and we'll get 843,287,808, and the theory predicts that this number will divide precisely by 32 to give precisely the number of bracelets without symmetry, and amazingly it does. The work is all done, and it's a small matter to tally the numbers and compute the relative frequencies. Relative frequencies here all reduced to a 1 in the numerator, giving the idea how hard it would be to get any kind of symmetry under the dihedral group of 32 if all the bracelets are randomly assembled. And that'll do it for the analysis of the skull bracelet. What a great math problem from an everyday item. I'm done with bracelet problems for a while, but there are other enumeration problems from everyday items that I'm thinking about for the next video.